Let's take a look at a couple more examples. And before we do the examples, we need to talk about something we've talked about previously, which is using integration to accumulate things. Because if you go back to the definition, remember that the definition of a definite integral is that it was the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I dx. We were finding the areas of rectangles, and then the integral sign replaced the limit of the sum. So a definite integral is adding together something. Up until now, it's always been adding together areas of rectangles. It still is. It looks a little different right now than it used to, because yesterday, when we were doing this, if we had f of x and that was g of x. F of x is the one on top. If we draw in a rectangle that's between them, which we did, the height of that rectangle. Now, before, we'd always go down to the x-axis, and the height of that rectangle would be f of x, right? But now we're not going all the way down to the x-axis. So the height of that rectangle is this y-coordinate minus this y-coordinate. So it's f of x minus g of x. Now, we weren't writing delta x yesterday. What were we writing for the width? Dx. Okay? So the area of one rectangle is that. We didn't think of it that way yesterday. Think of it that way now. That's the area of one rectangle. Add them all up. That's what the integral sign is telling you to do. Add them all up. Okay? Now, the integral sign is also telling you that you're adding them up and you're finding the limit of that as the number of them goes to infinity, but you're accumulating. Where is it? It's up here somewhere. You're accumulating these representative elements. The representative elements being rectangles. Okay? In a day or two, they won't be rectangles anymore. They'll be something different. But we're accumulating rectangles. Actually, areas of rectangles. But just to keep it simpler, we're accumulating rectangles. All right. So we've thought about integrals like that before. We need to think of them like that again. Okay? Number 59 on page 453. Write this one down. It is part of your assignment. The directions tell us to find the accumulation function, capital F. Then evaluate capital F at each value of the independent variable and graphically show the area given by each value of capital F. So, capital F of A, I think that's actually an alpha, we'll call it an A, equals the integral from -1 to A of the cosine of pi theta over 2 d theta. Now, if you'll look at what they ask us to then evaluate, they want us to find the value of capital F of -1, capital F of 0, capital F of 1/2. We could simply, to do part A, put a -1 right there. Oh, I bet you know what the answer is going to be. It's going to be 0, isn't it? All right, because we're not accumulating anything, because there aren't any rectangles between -1 and -1. All right, which would work great. We could do that. In fact, that's the best way to do part A. Part B, see, then we'd have to put a 0 in there work out the antiderivative, use the fundamental theorem of calculus to evaluate for 0, minus, evaluate for -1, get an answer. We can do that, though. But here's the trouble. Then they want us to do all that again, putting a 1/2 there. So instead of doing it, well, that one's going to be easy no matter how we do it. But instead of doing it 2 separate times to do part B and part C, a better thing to do is to get a function that this integral represents. Then all we got to do is plug in a 0 and evaluate. That'll be easy. Plug in a 1/2 and evaluate. That'll be easy. And by easy, I mean easier than working an entire definite integral problem. Okay? So what we're going to do then is we're going to find capital F and write it as, I want to say regular function instead of an integral function. Okay? In other words, I want to write it as a function without an integral sign in it anymore. That's what I want to do. Then we can evaluate for -1, 0, and 1/2, and 5, and 12, and -32, and anything else we want to. Okay? So, here we go. I'm going to take this integral. If I'm going to integrate the cosine of pi theta over 2 d theta, well, I'm used to integrating the cosine of u, du. Let's try that. Let's let u equal pi theta over 2, which is the same thing as pi over 2 theta, isn't it? And I want to think of it that way because that's easier to take the derivative of. Is it the derivative of pi over 2 theta, pi over 2? So du equals pi over 2 d theta. That's all fine and dandy, except I don't have a pi over 2 d theta. I just have a d theta. So I need to ignore it as incorrect, multiply by 2 over pi, and I'll get 2 over pi du equals d theta. Now, you don't have to write this down yet. Just help me figure this out. If I've done everything I need to do to make the substitution, I can make that cosine of u, d theta, can be 2 over pi du. Is that all I got to do? I got to change the limits of integration. So the substitution's going to work. Is that right? If this were an indefinite integral, that's the way I would rewrite it. All right? So all I got to do now is figure out what the limits of integration need to be. So if theta equals a, then what would u equal? Well, it would equal pi a over 2. So the new upper limit of integration is pi a over 2. If theta equals -1, what does u equal? Well, it equals pi times -1 over 2, which is -pi over 2. So that's the new lower limit of integration. So that means I can rewrite capital F of A to equal what I already had written out in blue, but now I'll put the new limits of integration on there. So it's 2 over pi times the integral of, your new lower limit of integration is -pi over 2. Your new upper limit of integration is pi a over 2 of cosine u du. All right, that's halfway complicated. Y'all follow me? Okay. What's the integral of cosine u du? Sine of u. Plus c usually. Plus c this time? No. So capital F of A equals 2 over pi times the sine of u evaluated from -pi over 2 to pi a over 2. So We evaluate. We evaluate first for pi a over 2. So keep that 2 over pi out in front, and then evaluate. So capital F of a equals 2 over pi times. That would be the sine of pi a over 2 minus the sine of negative pi over 2. Well, the sine of negative pi over 2, I know what that is. What is it? It's negative 1. So if I've got minus negative 1, that's plus 1. So capital F of a equals 2 over pi times the sine of pi a over 2 plus 1. Now, is anybody surprised that there's an a in our answer? You shouldn't be, because we're calling this thing capital F of a. There's got to be an a. I mean, it could be a constant function. It could. But, you know, that'd be kind of silly for them to go to all that trouble and it end up being a constant function. So, yeah, we expect to see that. Okay? Now, we're supposed to find the value when a equals negative 1, when a equals 0, and when a equals 1/2. So first, let's find the value when a equals negative 1. So capital F of negative 1. Oh, by the way, what's the answer going to be? It's going to be 0. We figured that out right off the bat. It's going to be 0. So capital F of negative 1 equals 2 over pi times the sine of then look, pi a over 2. Replace the a with negative 1. So pi times negative 1 is a negative pi. So negative pi over 2 plus 1. Well, just like a while ago, the sine of negative pi over 2 is negative 1. So in the parentheses, I have negative 1 plus 1. That's 0. 2 over pi times 0 is 0. Now, the directions also told us it says, and graphically show the area given by each value. So to graphically show the area, I'm going to graph that. And obviously I copy and pasted that out of something. But, you know, that's not real easy. F of A is not real easy to type into your calculator. So when you do, be careful. And A is, you know, use X. Okay? But it's kind of sort of complicated. Now, why is nothing shaded in? Because there's negative 1. There is no region when the left endpoint is negative 1 and the right endpoint is negative 1. There isn't a region. Okay? So the area equaling 0 hopefully makes sense to you. All right. Now, part A we could have done in about 2 seconds without going through that integration. But part B, though, capital F of 0. Instead of doing a whole integral with the upper limit of integration being 0, we've already got our function written without the integral. So I'm using this. I'm simply substituting a 0 in for a. So capital F of 0 equals 2 over pi times the sine of, well, pi times 0 is 0. 0 divided by 2 is 0. So the sine of 0 and then plus 1. Well, what is the sine of 0? 0. So 0 plus 1 is 1. So it's 2 over pi times 1. 2 over pi. Okay? Now, what's that look like graphically? Well, graphically, we started at negative 1. The right end point is 0. So we just found that area that I have shaded in, didn't we? Remember way back when we would put together integrals and shade in parts, and that seemed like they were always trapezoids or triangles, something like that back then. But we've done this kind of thing before. Part C. They want us to find capital F of 1/2. So capital F of A was 2 over pi times the sine of, where is it? Pi A over 2 plus 1. So replace A with 1/2. So if I replace that A with a 1/2. Now, pi times 1/2 over 2. When you simplify that, that's pi over 4, right? Multiply by 2 over 2, so you'll get pi over 4 when you simplify the theta part of that. So that's the sine of pi over 4, and plus 1. Anybody know what the sine of pi over 4 is? Yep, square root of 2 over 2. And, this one doesn't simplify all that well, but in the parentheses, if you get a common denominator, so think of that 1 as a 2 over 2, so you'd get the square root of 2 plus 2 over 2, and I wrote it as 2 plus square root of 2 over 2. And it's worth the trouble doing, because what can I do next? You got to be careful which 2's, right? That 2 is a factor, and so is that one. So I can divide out those common factors to get 2 plus the square root of 2 over pi as my answer. And then graphically, you started at -1. You went over to 1/2. So we just found the area of that shaded portion. Now, if they had chosen to give us an easy function, these problems wouldn't be all this bad. But think about it this way too. If they'd given us an easy function, then maybe we wouldn't need to rewrite this as what we're calling now an accumulation function. If it'd been easy to integrate, we could have just done different integrals, and maybe that would have been okay. But look, whenever our function is given to us with our independent variable as our limit of integration, we can work the problems this way. We can do the definite integral to rewrite our function as a function that no longer has an integral sign in it, and then to find the definite integrals, we just use that. Am I making any sense? Doing this was the same thing as finding the integral from -1 to -1 of the original function. Doing this was the same thing as finding the integral from -1 to 0 of that original function. Doing this was the same thing as finding the integral from -1 to 1/2 of the original function.
Basically, what we're doing is we're doing a definite integral.
Right. We're doing a definite integral with variables in it, which then gives us a function that we can evaluate for different values.
And that function is found after section off basically the line.
That's right. Because to find this shaded area right here, we could have done this instead of that. But doing this would have meant doing all that. Okay? So it's like we do it once. So it's like what we did with derivatives early on. We would find a derivative, use it as a formula to find more than one slope. We're finding the integral using our new function as a formula to find as many areas as we want. Does that make sense? The only condition is this. What's the left end point of each of these little regions have to be? Has to be -1 because that was our lower limit of integration. Okay? Yeah. All right. Any other questions? Let's do another example. Number 66. There was a time when the AP test was in love with oil spills. Estimate the surface area of the oil spill using, we're just going to do the trapezoidal rule. Anytime the directions tell you to use Simpson's rule, we don't do that. All right, so how on earth is the trapezoidal rule going to apply to this? Well, because we can make trapezoids. Oh, wait, I can be fancier than that. I can use different colors. So there's one. Oops. Let's round that, square that off. There's one. There's one. So forth. Now, those of you that went to the review session on Saturday, what happens right out here? Triangle, because the base, well, I'll call it B0, that original base there isn't one, is there? Okay, so, but we can do that. So let's remember how the trapezoidal rule is going to work. Okay? All right. Remember that the bases are the sides that are parallel to each other. The height is a segment that's perpendicular to each of the bases. So the height of each of these is 4 miles, isn't it? Okay? But look, here's your general formula. Area of a trapezoid equals 1/2 times the height times the sum of the bases. So for that first yellow trapezoid, that'd be 1/2 times 4 times, and then the first base wouldn't exist, and what would the second base be? 11, right? Now, we've done this in the past by simply finding the area of each trapezoid and adding them all up, but that's a bunch of trapezoids. There's an easier way. There was the trapezoidal rule, which I didn't make you memorize, and I'm still not going to make you memorize. We can figure it out. Because this non-existent yellow base, that's only in there once, right? But that next base, that 11 miles, isn't it a base of the non-existent yellow trapezoid, which is really a triangle? And isn't it also a base of the red one? So it's in there twice, right? It'll be a base of the first. I'm going to call it a trapezoid, even though it's a triangle, okay? You can actually define a trapezoid so that a triangle fits the definition. So we just did by magic. Triangles fit the definition, okay? Then the red one base is 11, the other base is 13.5. So the 11 is in the yellow one, and it's in the red one. Then look at the red and the blue one. The 13.5 is a base of the red one and the blue one. And then the 14.2 is a base of the blue one and the green one. So that's in there, well, that's in there once. So let me not circle that. So the 13.5 is in there twice. The 14.2 is a base of two different ones. So is 14. So is the other 14.2. So is the 15. So is the 13.5. and then you get down to the, another one that would actually be a triangle. So, so in every single trapezoid, that's 1/2 times the height, isn't it? So factor out 1/2 times the height. All right? The very first little yellow base was a 0, so I put 0. Then 11 was part of the yellow one and part of the red one. So 11's in there 2 times, so 2 times 11. Plus, and then 2 times each one of them till you get to the end. And then we'll pretend there was a yellow triangle at the other end, and that very last base then would have been 0 on it. Now, do you see how what I have showing actually is the sum, the accumulation of however many of those trapezoids? Do you see that? Because all I did, that 1/2 times 4 is in every one of those trapezoid areas. Since it's in every one of them, factored out, put it in the front. So when you're going to estimate areas with trapezoids, is it a good idea to make them all have the same height? Oh yeah. Yeah, otherwise you do have to find each individual one, and you can't, shortcut it like we're doing here. All right, you guys with me? Another thing that the AP people used to be in love with, sewage. So this was just as likely to be a big sewage spill as it was an oil spill. And I had a hard time with those problems. I just couldn't get past it. Oil, fine. Kill a few dolphins. I will live. But throw a polar bear in there just for fun. I'm kidding. Y'all are looking at me like I'm the most evil person that's ever lived. That was a joke. And then this is one where you don't need a calculator, but man, I want to use a calculator. It was a joke. On the AP exam, you can leave it like that. For me, you write it like that. And talks about further parts. You're going to waste a lot of time punching things in on your calculator if that's what you leave it as. Yeah. And I get it, and I guess I'm sort of glad that on the AP test you don't have to simplify everything. But I'm also a little offended when they tell you over and over again that the reason they do that is because you guys suck at algebra. I mean, that one lady said that both sessions. And you guys don't suck at algebra. You don't make it to calculus if you suck at algebra. You make it to algebra. So, now, on the other hand, it is kind of nice that you don't have to take the time to simplify that answer. It's the time that's a factor. That's the big deal. Okay? All right. You with me? All right. So, page 453, 33, 35, 37, 43 through 51 odd, 57, 59, 61, 65, 66, 71 through 74. Yeah, if you don't want to write the assignment down, I'd do 33 through 74. Probably faster. All right, what would you like to see from yesterday's work? 5, 6 first, huh? You want me to go backwards? Is that possible? All right, number 6. The directions say to set up the definite integral. All right, so we will. We'll even solve it if you want to. So we've got f of x equals the quantity x minus 1 cubed, and g of x equals the quantity x minus 1. I need a picture of this. All right, so we'll call y1 f of x. So that'll be parentheses x minus 1, close the parentheses, put an exponent of 3 on it. And then y2 will be x minus 1. And we'll graph that. And let's change the setting a little bit. All right, that's a little bit easier. Okay, now, there's some trickeration going on here. Because when you start off at the left point of intersection and move to the right, y1's on top. The f of x is the top curve. Then whatever that point of intersection is, then it switches, and the g of x is the top curve. So to find the area between those two functions, I've got to do it in pieces. I've got to find the area with f of x minus g of x, and then add to it the area found by doing g of x minus f of x. So that's what gets me set up over here. So the first region is formed by, or each little rectangle will be formed by f of x minus g of x, but in the second one, it's g of x minus f of x. Make sense? Okay. Now, to get your points of intersection, you would set those two functions equal to each other and solve them. Or, since you've already got it graphed, second calc, intersect. So first curve, there's pretty good. Second curve, there's pretty good. We'll use that as the guess. And sure enough, 0 is the x-coordinate of that first point of intersection. Okay? Now it won't do that. So then let's find the next one. So let's find the next intersection. Okay, let's move that right there, right there, right there. So 1 is the x-coordinate of that second one. So the first region starts at 0, goes to 1. So the integral from 0 to 1 will, of f of x minus g of x dx will find that area. So that means the second area, second region starts at 1. Let's find that last point of intersection. And it's 2. So now I know how to find the red one, and I know how to find the blue one. And then I got to thinking, hey, are those two regions the same size? Because if they are, all I got to do is find the area of one of them and double it. Yeah, if you don't know it for a fact, don't guess it. Yeah, as far as to set it up, I would consider that to have it set up. Okay? Genius.
idea of some.
It has nothing to do with the fact I have a solutions manual. Nothing to do with that. All right. And so, simplify it as far as you can. Stick, even if you stop, well, I take that back. Don't do that. Don't stop there. Put the x minus 1 quantity cubed and the x minus 1 in. But I would still take that one as two separate integrals as long as you put those in. Okay? All right, number 5. Nobody needs to know number 5. We done seen that one. Is that right? Is that the proper way to say it? We done seen it? Oh, man, I'm recording that, too. All right, anything else you want to go over? 23. All right, 23. Let's see. The directions say, sketch the region bounded by the graphs of the algebraic functions and find the area of the region. So we have y equals x, and y equals 2 minus x, and y equals 0. So here's the graph of y equals x. Here's the graph of y equals 2 minus x, and here's the graph of y equals 0. So that's how we know that little shaded part is the region we're after. Okay? And here's the trouble, is for a while, the region is bounded with the blue graph on top, and then for a while, the region is bounded with the red graph on top. So we're going to have to work this as two separate integrals. We'll need to find the blue area, then the red area. Okay? Does that make sense? All right, so I need to know where they intersect. So I set them all equal to each other, and I get 3 points of intersection. All right, I knew the x equals 0 because, y equals x and y equals 0 got to intersect when x equals 0. So I knew that one right off the bat. Then find the other. So set x equal to 2 minus x, get that one, which is right there. And then set 2 minus x equal to 0 to get that one, which is down here. Okay? So I need to make the integral from 0 to 1 of, then it's the blue one on top. So f of x is x minus, then the one on the bottom, the green one, y equals 0. And then the integral from 1 to 2 of, this time it's the red one on top. So f of x is this time 2 minus x minus g of x, the green one, still 0. And then we can work it out from there. And I tell you, if this weren't in a calculus class, how else could I have found those areas? It's a triangle. Is that fair game? Yeah. All right, because look, the directions on this one didn't say, like the 1 through 6, didn't say to set up the definite integral. So if you realize after you've graphed that, you've got a triangle, you can find its area just by finding the area of the triangle. That's perfectly acceptable. Okay? On the AP test, I doubt, well, I don't know, no, because they give us this kind of thing. They'll do this and give us, So yeah, if you can do it as a triangle, do it as a triangle. If you have time, you might want to go back in and say, I did this geometrically. Here's how I would do it calculusly. Using calculus. Calculitically. I think that should be right, though. I think calculitically should be the correct way to say that. I don't know, did we? Oh. Anybody try to do number 23, writing those as functions of y instead? You can. All right, your little rectangle would be like that. So then the curve on the right is always this one. You just need to write it as a function of y. The curve on the left is always this one, just consider it a function of y. Your limits of integration need to be the y coordinates, so 0 here, 1 here. Works out quite nicely. And then, of course, the easiest way, geometry. So the easiest calculus way is to do them as functions of y. All right, where is 12? Let's get that on here real quick. Ooh, that's fun. So on 12, what were we doing? Oh, we just had to make the graph? Okay. Now, they might ask you on the AP test to do an integral like number 12, but probably with your calculator, if you need to get the definite integral. Indefinite, you need to be able to do it. Definite, probably a calculator question.